I was talking on mute. Now you could probably hear what I'm saying. It's a little bit new. We got a new banner at the top there. So we are live now. Chapter 7, text clustering. And so a lot of what we're going to be talking about, we have gone over. Let me turn the slide on so you guys get a little bit more light because it's a lot going. Oh, didn't mean to do that. So we got the light on, we got the blue background. We are back to what we know. We are talking about text clustering in this video. So chapter 7, text clustering, we're going to be leveraging a lot of what we've learned in the previous chapters, specifically embeddings. And if you are familiar with statistics, right, we also have things like k-means clustering. There are other types of clustering like Baynes and all that. We don't have to go too deep into that. But this is going to be a shorter episode where we are going to be leveraging embeddings and k-means clustering to split our text data set, right? Remember the travel data set into different clusters with semantically similar sentences, right? So if syntax is the words that we use or how we do it, right? The semantics is the what, right? What is the gusto behind the sentence? So what is this? This is the vertical. Sorry, let me select the stream right here. All right. Okay. So as the amount of unstructured data increases, organizations will want to be able to derive an understanding of its contents, right? So the more data an organization gets, the more they're going to want to understand what that data represents, what are the features that we need, features being the descriptive factors, right? So a feature of me is height, gender, hair color. Those are features, right? You can think of them sort of like attributes. What is it that we are going to be passing through to these models, right? So if we're trying to figure out, hey, what is the best clothes for someone that fits my description, we're going to need to know my height. We're going to need to know how long my legs are, how long my torso is, how wide uh, of a stature I have, how wide my arms are. So those are these features, and we're going to want to know and understand the contents behind things, right? So that we can feed that into the model, so the model can cluster. Hey, you are this tall, this wide. You're going to be more in this area of clothing, right? So one example would be to discover underlying topics in a collection of documents so we can explore trends and insights. So if we go back to the example that we've been using, right? These transportations, right? We want to know, what are the underlying topics? What are the underlying semantics? What do these sentences have in common? What is the gusto of these sentences? And so another could be for businesses to segment customers based on preferences and activities. So again, back to the closing example, we want a way to cluster either sentences or topics based on what is in the content itself. So these kinds of tasks fall under a category called clustering. You can think of it as even, unloading a bag of M&Ms or Skittles, right? You might want to put them in different groups of the same colors, right? That is clustering. So in machine learning, clustering is a process of grouping similar documents into clusters. Just like M&Ms, you want to cluster them into classes of similar colors. Colors being the semantics, right? They share what do they share, right? These M&Ms share colors. You could go based on size, you could go based on wholeness, whatever it may be. This is what they share. And so it is used to organize a large number of documents into a smaller number of groups. And it lets us discover emerging patterns in a collection of documents without us having to specify much information beyond supplying the data, right? So you want to structure the data. You want to make sure the data is clean so that it can be passed through, but you also don't want to have to go through and say, okay, this guy's this tall, let's move him over here to this clothing. No, you want to be able to just pass the data through and the model be able to cluster itself. And so in this chapter, we're going to learn how to use those embeddings that we learned from previous chapters to partition a text data set into distinct clusters of semantically related sentences. So what we're going to do is we're going to use embeddings to partition a text data set into a distinct cluster to semantically related sentences. We are going to put these sentences into related groups. I need to fix the screen capture because it is frozen again. I don't know why this keeps happening. So we're going to uh, flip here and then flip back. Now you can see that it's not frozen anymore. So step-by-step guide. We're first going to start out with that same example that we've used in the previous episodes, right? The previous chapters, we have this list of 9 data points related to travel information, whether that be flying, whether that be ground transportation. And these are the data points, the data set that we are going to use to practice clustering. And so step 1 before clustering is we want to embed the text, right? We embed the document using the same get embeddings function as before, but if you remember, there were 4 input types. And so in this input type, we're going to be using clustering because we'll use the embeddings for clustering. And if you recall, these embeddings are these numbers, right? So there's each text field, each word, right? They can be embedded based on the text itself, right? And these embeddings are a set of numbers to plot these words, these sentences in a graph, right? Think of it as a graph. Remember, we could have a 2 by 2, right? And we can plot it based on length or different things. But most times with these MLs, with these AIs, with these models, these embeddings are going to be very large, right? Over 1,000. In this case, in this example, I believe it's 1,024. And so, well, we are 3D people. We only live in a 3-dimensional space. How do we even envision a space with over 1,000 dimensions? And so we don't have to worry about that because the embedding model will be doing that for us. But you can think of it as 1,000 different ways to rank these sentences, these words, and it understands how close they are based on these 1,000 different ways to categorize what we're looking at. Right? You can even think of this. Imagine each sentence and word as a picture. Right? If you have a picture in front of you, you could say, okay, well, we have what's in the picture, the colors of there's 20 different things in the picture. Each color could be different, right? So you can see how it can get very big, very fast. And the same can be done with words. And so what happens is we use this get embeddings to make it available to then begin to cluster. It makes these embedding parameters easier to pass through for clustering. Okay, you're following me thus far. Step 2 is to then cluster those embeddings. We want to say, look, okay, let's look at what's been embedded and see out of these embeddings, which share the most in common, right? Based on those numbers, which ones are more closely related. And so implementation-wise, we're going to be using the k-means algorithm to cluster these data points. We can go into more about what this means, what these k-means, what these different ways of clustering are. You could cluster, let's take the M&M example. You could cluster based on size. You could cluster based on color. You could cluster based on the pieces that are there, but that's just what we're clustering on. If you think about how to cluster, if we're going to the M&M packet, you could dump all of them on the table and then cluster. You could take out one by one and place them in specific clusters. You could dump half out, put them in clusters, and then dump the other half out. So you can already see how there's many different ways to cluster. And the same goes for these clustering the embeddings, right? We can use many different clustering algorithms to put these words in these sentences into different places, right? And so other than providing the embeddings, the only other key information that we need to know, that we need to provide to this algorithm, is the number of clusters we want to find. All right, so again, we have these embeddings. There's over 1,000 different points per data point, right, that we are going to embed. We're going to provide a number. Then we're going to select, in this case, the k-means, we're going to select how we want to cluster them or what way we're going to cluster it. So think of it as we're just pouring everything out and clustering what we have in front. And then now we need to find, okay, how many clusters do we want? Do we just want 2 clusters? Do we just want to cluster based on color? Do we want to cluster based on color and size? And so those are things that we have to think of before we're going forward, right? In this example, we are only going to cluster based on 2 things, right? And we'll see as we move forward. So this is normally larger in actual applications, right? There's going to be many different data points. And so we can't just cluster based off 2 things. But since our data set is small in this instance, it's 9 data points, we'll set the cluster to 2, right? So we're going to have 2 different groups per se. So number 1, we're picking the cluster. In this code, n clusters equal 2. N could be any number. In this instance, we're setting it to 2. we're then going to cluster the embeddings. So we're going to be using the k-means model. And so k-means is, so you can see the n clusters equals n clusters. Of course, it's going to equal itself. And the classes that we're going to use is this k-means model, and then we're going to use it to fit those embeddings into our space, right? And so we're going to store those cluster assignments. So again, what it's going to do is it's going to say, okay, cluster it, either put it into cluster 1 or cluster 2, and put that into a list. Okay. And so step 3, after all of this is done, after we've done the clustering, we want to plot it. So this is for us to visualize, right? So where do they sit? If we can simplify all those different clusters from 1,000 down to 2, so we can plot it and visualize it, how are those text fields going to present on a two-dimensional plane? And so what we see is the plot below, right, shows those clusters that the algorithm returned. And so it looks to be really spot on with what we've seen in the previous chapter. If you go back to chapter 6, this is the exact same example from the embeddings, but you'll see on the right-hand side in the orange, you're going to have those ground transportations, right? If you read it, show me a list of ground transportation, show me Boston ground transportation and what ground transportation, you can see not only do they share the same color, right? That is the cluster, but they're also on the right side of the plot graph, right? So they are, in essence, very similar or more similar than those on the left-hand side, which are related to air transportation, right? It could be something else, right? Not all of them are air transportation. Like the last one, I like the lowest fare from Denver to Pittsburgh. We assume that it's talking about air flight, but we don't know, right? And so as we can see, yes, we have 2 clusters there, but if we had set the cluster to 5, we could cluster this 5 different ways. And that might not be as specific as we're looking for, right? Just because you say to cluster, it doesn't mean those clusters have anything in common. The model isn't as intelligent to say, give me only when these are, you know, two squares apart. We would have to provide that instruction. But you can see using those embeddings, right? Using those characteristics that we were able to parse through, right? So we take our data points, we pass it through an embedding model. The computer looks, right? The model looks at, okay, out of those embeddings, which ones have a 1? Which ones have a 2? Which ones have a 3? And then it takes it and it goes, okay, based on how I want the cluster, how am I going to sort these? What I'm going to do is I'm going to say, okay, all of those that share a 1, we're going to put over here. All of those that share a 2, we're going to put over here. And so you can see how these clusters come together. And so this was a very, very quick overview, but in this chapter, you can see how the clustering starts to come together, right? You learn how to cluster a data set of sentences, and you get to observe that each cluster corresponds to a particular topic, right? And so this will slowly start to form how when we pass queries through, how we pass prompts through to these LLMs, how their responses can be geared towards those queries, right? Those prompts, because what we're passing through, it's going to parse, it's going to embed that query and say, okay, now I want to go look at the clusters that share similarities to this query. So if I say, hey, what is the ground transportation? You can see it's going to go straight to those orange dots and say, okay, these are our ground transportation clusters, right? So where do we find ground transportation? What other clusters share similarities with these clusters? And so that is how it's going to be able to provide that response. Okay. Chapter 7, text clustering. So I know this was a short stream, 15 minutes. So I'm going to use this time to go into something a little bit more, right? Concurrent viewers 2. What up, Zoe? Let's check this out. So something I want to show, something that has been blowing up in popularity recently, is something called AI XBT. And if you're not familiar with AI XBT is an AI agent that is hosted or provided on the Virtuals protocol. You can think of this as a meme coin, right? It is a meme coin. It's not providing you any benefit by buying the token of AI XBT. But what AI XBT's goal, what their goal is they are going, or they scan, right? They scan Twitter, they scan social media, and based off the sentiment that they are able to scrape together from these social media platforms, it is using that to predict or to recommend what is the most likely outcome or what it has captured in the past. So if we look here, Gandhi just hit record week with whatever's going on, single vault, blah, blah, blah. And so it's providing the market sentiment, what has been going on based on what it has been scraping together. 1 year ago, BlackRock's IBIT and spot ETFs went live. Since then, they've accumulated over this 1 million Bitcoin worth $95 billion. And so not all of the output is garbage, right? You can tell it's automated, it's a bot. Some of the inference that it puts out there is again the sentiment that buyers have, right? So sometimes it just simply conjures up, almost hallucinates, but simply conjures up what it has been fed and spits it back out. So it might not totally be accurate. And there have been some questions surrounding the accuracy of this model. But even here at the bottom, you can see no roadmap, pure comedy, TEDism pushing 3 discussion clusters with consistent engagement past 4 days, right? This is a model. This is an AI. This is an LLM conjuring this up and putting this out there. And so a lot of the hype, if we go back, a lot of the hype behind this token, you can even look at the price. It is 50 cents now. Where were they 3 months ago? Near 2 pennies, right? So it has more than 20x in the last 3 months. But all the hype behind this coin, all the noise, and you can even see that there's been articles written about this. CoinSpeaker, Forbes, CCN, right? All of these different media outlets have been writing about this, not because they think it's a good investment, but because it has never been done before. It hasn't been seen before. It hasn't captured audiences' attentions like this. And so even going to the virtuals protocol, right? The virtual protocol or the virtuals protocol is a protocol on the base network, the base chain, right? The base chain is a L2 owned and operated by Coinbase. Virtuals lets people host these AI agents so that they're able to have coins, gain funding. People can buy in if they have other use cases. And so what AI XBT is, we talked about, it tracks crypto Twitter discussions and leverages its proprietary engine, which I'm just going to assume is either Gemini or ChatGPT, to identify high momentum plays. And so it's using the market analysis, the sentiment from the market or from crypto Twitter to make predictions. Open widget, such as what is going on? How do I fix smooth streaming? Let's see. Connection. Poor. Oh, let's figure this out. It says I don't have a good internet connection, but hopefully that's not an issue. But I will say this is going to be my cue to log off. Stay tuned for chapter 8 next time. I know these have been brief. I want to get to do them more. Essentially I'm learning this. I don't want to say all at the same time, but some of these LLM University articles, it helps me go into depth, right? I get to speak out loud. I get to hear myself say it, and hopefully I'm helping you learn along the way. And so again, if you're not familiar with Pear Does, you're not familiar with what we've been doing, we're just going through the multiverse, right? AI, crypto, stocks, you name it, everything that is interesting to me, everything that I find interesting, I want to bring to you. I want to make it in a digestible format so that you understand and can comprehend these complex subjects. And with that, I bid you all adieu. Please tune in next Friday. I promise we'll be early in the AM this time. If you want to see more, if you like these streams, please reach out. Please let me know. And we can try and get more on the calendar. But right now, we're going to keep it to once weekly. Go check out the shorts and go follow Pear Does on social media platforms. All right.